Okay, everyone, I had mentioned in the introductory video that I was going to try to re-record the multiple regression video. So here I am re-recording the multiple regression video. This is going to be a little bit long, so settle in. It'll take us about 30 to 35 minutes to get through all this. And I want to go through the example that I've provided to you. And the reason why I want to go through this is because the data camp chapters really didn't prepare you for the level of work we're doing now in some of the scripts that I'm giving you. So what I want to do is just take a little time. I may skip over some stuff if I don't feel like it's really all that important, but I want to try to explain each one of the commands so you get a better idea of what it's doing. So here's a couple things we're going to do. First off, we are going to load up a script that I've given you. It's called MultiReg for multiple regression. And the second thing we're going to do is we're going to load up a file called Toyota Corolla. And Toyota Corolla is a list, basically it's a pretty large file actually. It's got a number of rows, a number of columns, and we're going to do some manipulation with the data that is in that file. We are going to limit it down to 1,000 records. We are going to eliminate many of the fields that we don't feel like we can use or need or really want. And then we're going to do some processing on the remaining fields. We're going to divide it into a training and validation set. And then after we were divided into a training and validation set, I am going to work through a process of setting up, first of all, validating fields and then setting up a multiple regression model and seeing what we get. So here we go. We're going to go ahead and start right directly from the screen, the R console, just simply because why not? There's not a lot to do really in PowerPoint. I'm going to go ahead and open up the script. And the script, as you can see from your Canvas module, it's called MultiReg. So I'll just go ahead and pull that in. And that opens up the script. And like we did last time, I'm just going to go ahead and pop this over into another window. I'll expand that window a bit so that we can kind of see what the script is doing. Look at the script. The first thing in the script is just a sort of a header. And you'll see, as we've seen in the past, when we have a script where we have pound sign is comment. So that means anything after the pound sign, after the pound sign, hashtag, whatever you call it these days, is going to be ignored by R. So I've put a lot of comments in this file, hopefully to help you understand kind of what each of the rows is doing. So the first thing we're going to do is going to read in the data file. And I told you the data file is called toyotacorolla.csv. It is also in your Canvas class or Canvas module. And so you're going to have to make sure you download that file and put that file into your working directory. And if you don't remember, to find out what your working directory is, do getwd, getwd, open paren, close paren, and it will tell you what your working directory is or your working folder. And you can drop the toyotacorolla.csv file directly into that folder. Once you have it there, go ahead and run that command to actually load that file up, and you'll see that it has loaded the Toyota Corolla CSV file. Now, I haven't really told you much about this file, but let's see, let me get over to where I need to be. But it's 1,436 rows and 39 columns. So I ran the dimension function on car.df. You can see that I dropped this file into a data frame called car.df. So now I'll just refer to everything in car.df. So 1,436 rows, 39 columns. I can tell you right now, most of those columns are not anything we're interested in. So one of the commands that's going to be early on in our script is to get rid of the majority of those columns. Just pare down to just a few that we can actually use. We will drop the data set down from 1436 down to just an even 1,000, and then we'll divide that data set up into 600 records that are training data and 400 records that are validation data. And so that's getting us back to this idea of having a training set and a validation set, just to make sure that when we build a model, we validate the model. All right, let's continue on in our script. So we've read in the data file. Let's get rid of that because that was my mistake when I wasn't in the right screen. All right, now we're just going to use the first 1,000 rows. So we're going to take car.df, the data frame, which currently has 1,436 rows in it, and we are going to set it equal to the first 1,000 rows and all columns. So this is, you've learned this in the chapters of how to go into a data frame and identify specific rows and specific columns. So here we're going to go 1 to 1,000 and all. When you don't specify anything, it takes all of the columns. And that's going to go into cars.df. So we're basically just going to overwrite car.df with the first 1,000 rows. We'll go ahead and do that. And now we're down to 1,000 rows, okay? So now we're going to get rid of all of the extraneous columns that we don't want. And so we've gone through the data set and Somebody else did this for you, so you don't need to worry about it. But we did a view command, and we looked at all the fields that we wanted. We found out that the fields that we wanted were in columns 3, 4, 7, 8, 9, 10, 12, 13, 14, 17, and 18. So what we're going to do is we're going to create a variable. The variable is going to be a list of these columns, and we use the C command to actually specify the list of the columns, and we drop that into selected.var. That's just a variable that holds those numbers for now. So we can go ahead and go through that. That variable is set. Now we can use that variable to partition the data into training and validation sets and do it in such a way that we only isolate out those particular columns. So the first one we're going to do is we're going to build the partitions. 600 of the data points are going to be set for training data, and 400 are going to be set for validation data. So the way we're going to do that is we're going to create what's called a training index, and the training index is going to be equal to a sample. Now the sample is, we're going to look at the matrix here of 1 to 1,000, and we are going to pull out a sampling of 600 of them. Okay, so that's what this command, what this function is doing. It's saying go through the data set and give me numbers ranging from 1 to 1,000. Give me 600 of them. So maybe I pick 1 and I pick 2, but I skip 3 and 4 and I pick 5 and so on and so on and so on until I have 600 of 1,000 numbers dropped into this index. So at this point, this index only holds numbers, 600 numbers from 1 to 1,000. Okay. Then I'm going to go through and I'm going to set up 2 more data frames. This first data frame is train.df. That is my training data set. And it's going to be set equal to the data frame of car.df using the training index, right? So that's my rows. Remember, the rows come first. When you have the square brackets, you got the rows. And the rows are those numbers, those 600 numbers from anywhere from 1 to 1,000. And the second variable I'm going to use is my selected variable that I built up here. When I did selected variable, just give me all of these columns. So the rows are set to a random 600 from 1 to 1,000. The selected, or the columns are set to the selected variable that I set up here. So that is how I'm isolating out just those columns for some 600 rows, anywhere from 1 to 1,000. And that creates my training data frame. My validation data frame is set up by doing the exact opposite. Looks very similar, but it is the exact opposite. So I'm going to pull from my cars data frame anything that is not in my training index. Okay, to create my training index up here, that holds the 600. The ones that are not in my training index are going to be the 400. So anything that's not in my training index, and the same selected variables. So what I wind up here is 600 training data set, 400 validation data set. It was a pretty creative way for us to be able to sort of break those apart and set those up such that we can actually isolate out the specific records, the specific rows and columns that we want for the training set and the validation set. Okay. Now that we got that done, we're going to try to figure out from the training data set, we're going to try to figure out what it is we have that we might want to look at for multiple variables that we use in our multiple regression model. So got a comment here that says, now determine the fields that might work for our model. And we're going to create a subset of the numeric fields. Those are the ones that we originally pulled out up here that are now in our training and validation data set. We're going to create a subset of fields that we think might actually work as a regression in our regression model. So we're going to take a look and we're going to do something called correlation column. Correlation column is really just an opportunity for us to sort of, well, first set a variable and then run correlations kind of every variable against every other variable. And it's a cool way for us to see what's correlated and what's not correlated in just one command. So we set up a variable called correlation columns, and that's going to be set equal to this list of fields 1, 2, 3, 5, 8, 9, 10, and 11. And then we're going to check the correlations by running correlation. Correlation is a function. Into correlation, we're going to put the training data frame set. So we're just going to grab the training data frame set, and we're going to look only at whatever we put into the square columns. So in the square column, or square brackets, I'm sorry, in the square brackets, we specify all rows. So it's going to look at all 600 rows. Remember, when we don't specify nothing, we really specify everything. So it's going to look at all 600 rows, and it's going to look at whatever we put into the core column value as far as the columns that we want to look at. So out of the training data set, run a correlation on every row but just those columns. So let's go ahead and run through that. Actually, I've got to catch up a bit here, don't I? I'm talking too much and not actually executing these commands. That sets the variable. And here is our correlation. Boom. Okay. So these fields, 1, 2, 3, 5, 8, 9, 10, 11, correspond to price, age, kilometers, horsepower, cubic centimeters, doors, quarterly tax, and weight. That's what those variables are. So what we're doing now is we built like a 2x2 matrix where we can actually look at how is price correlated with price. Well, price correlated with price, as we would well expect, is going to be 1.0. It's correlated with itself. So that's basically useless information. But price correlated with age, well, that's going to have a negative correlation of 0.8695. That makes good sense because the older the car is, the less it's worth. So they're going to go in opposite directions on an almost predictable and consistent pattern. When we compare price to the number of kilometers, that too is probably going to go in a fairly consistent and negative pattern, and it does. And it's not as good as the age of the car, but the higher the kilometers, the lower the price. Horsepower, that's a moderate correlation. Cubic centimeters, pretty small correlation. The number of doors, pretty small correlation. Quarterly tax, it's not a great correlation, but weight is a pretty good correlation, which basically means the bigger the car, the higher the price. The bigger the car, the higher the weight, and the higher the price. So this is all in an effort for us to be able to look at what would be good predictors. And the things that are going to be good predictors are the things that are going to have a really good correlation to the price, because if it has a really good correlation to the price, its behavior is predictable relative to the price. Consequently, we can look at it as a predictor. Now, age will look like it would be a pretty good predictor because it's got such a high correlation of 0.87. That's pretty high, but there's still a little bit of room for error there. The number of kilometers, that's a moderate correlation, let's just call it moderately high correlation. Horsepower, cubic centimeters, doors, and quarterly tax, not very good, not very useful. Correlations are small, low, or almost non-existent. The weight, however, is also kind of on par with kilometers at 0.58. It's actually a little higher. It's positive, so it's got a different direction, but it's still a reasonably good predictor. So what we could do here is we could say, let's try to consider age, the number of kilometers on the car, and the weight of the car in combination as a predictor of what the price is likely to be. So that's why we ran the correlation, so we could see what was correlated. And now we can get to a place where we can start thinking about building our model. So back over here on the script, I've already sort of tipped off what we were going to do, age, kilometer, and weight as the three potential fields that we will use to build our model. We're going to do a little bit more work first. This is just fun work for fun. First thing we're going to do is we're going to run some plots. So we're going to run some plots to see how well each one matches the price variable. So we're checking each independent variable, and these three variables that we've selected up here, age, kilometer, and weight, are what we're considering to be our independent variables. They will be the ones that impact price, and price is our dependent variable. So we're going to run plots to see how well each one of the independent variables matches the price variable, and we're checking the independent variables against the dependent variable. So we're going to run age versus price, kilometer versus price, and weight versus price. And here are those plots down here. So we run a simple plot command. We are comparing price. The little tilde sign means price versus age. This is the age variable. And then we don't have to say cars.df $price because we specify here the data set is train.df. Okay, so we're actually not looking at cars.df, we're looking at train.df. So we're looking at the training data. Let's look at the first one. The first one shows us a plot. Now this is the price versus the age of the car, and it's a negative correlation. It's a pretty strong negative correlation. This is not terribly surprising. It's kind of what we've already seen. So it's a little bit of a duplicate of what we've seen. And it's just another, I'm showing it to you as just another method that you can use to validate that this is actually possibly a very good predictor. The other one we're going to look at is weight of the car. Well, first of all, we're going to look at the kilometers of the car. Kilometer versus price. So let's go ahead and look at that. That one also looks like a negative correlation. It looks like it's fairly good. It's not as good as the age of the car, but it's still fairly good and could be used as a predictor. Later on, we'll see plots where there's no connection. You can see they're just kind of a scatter. And then the last one we're going to look at is the weight. And the weight is, now that's positive correlation. It's positive correlation because the higher the weight, the higher the price. So it's kind of going in a different direction, but it's still, if you were to put a trend line through this, you could see that most of those data points would fall along that trend line. And so that would still be a pretty good predictor. So now what we're going to do is we're going to take a look and we're going to compare the independent variables against each other. And why would we do that? Well, when we're doing multiple linear regression, we can actually over-predict or we can over-represent. And we do that when the variables we're using as independent variables, for example, age, kilometers, and weight, are very tightly correlated with each other. And if they're very tightly correlated with each other, then what we're doing is we're over-representing the predictor values, and we can mess up our model if we do that. And it's called collinearity. So we're going to check the independent variables against each other to check to see if we have dangers of collinearity. And if we have dangers of collinearity, we might have to knock out one of our variables from our model. Instead of having 3 variables, we would just have 2 because we don't want to overrepresent the predictors. So let's go ahead and take a look at those. And we'll plot them first, and then we'll run correlations on them. Plot is just for visual. The correlations will actually tell us what we really want to know. So the first one, that one looks like it might have some measure of a positive correlation. This is age versus kilometers. The higher the age, the higher the kilometers. The higher the kilometers, the higher the age. That makes sense logically, but I don't know the extent to which there's enough of a real true correlation between those two, because there's a lot of scatter around what might be a trend line here. There would be a lot of scatter around it. I'm not sure if we need to worry about collinearity there. But let's take a look at the next one. That one's a mess. I mean, you can't really draw a trend line that would have really any sort of meaningful use, either positive or negative. It would most likely be a negative trend line, but it's still pretty scattered. And so in the third example, we have a complete mess. I mean, basically, it looks, you can't even tell if it's positive or negative. It's probably most likely positive. The weight and the kilometers, those really are not related variables. So even though weight individually could be a good predictor for price, and kilometers individually could be a good predictor of price, they're probably not suffering from any collinearity in the sense that they don't really correlate with each other. Well, that was visual. So let's go ahead and actually run the correlation. So we're going to run correlations, core.test. We're going to look at train.dataframe price and train.dataframe age. We're now looking at them, the independent variables, and we're calculating true correlation coefficients. So let's go ahead and do that. Okay, so in the first one, we ran the correlation. This is actually a really duplicitous of what we did earlier. Because what we did earlier, if you remember, we went up here and we ran this table. This is just running the individual correlations. It's complete busy work because we already have this information. We already know that there's a negative 0.8695 correlation between those two variables. You might even, if you want, and I would be fine if you did it, comment these out because this is just doing something that we've really already done. I'm just going to blast through them fast. What I'm more interested in, though, is testing the independent variables. So what is the correlation between the age and the kilometers, the age and the weight, and then the kilometers and the weight? And that's going to tell me to what extent do I need to worry about collinearity. If those correlations are really high in either direction, then I might have a bit of an issue. So the first one is going to give me a 0.544. Now that's considered to be a moderate correlation. Anything 0.54 or anything around 0.5 would be a moderate correlation. And we might be concerned about this, but at this point in time, I'm going to say, let's just let it go. Let's just let it go for our example. The next one gives us a 0.48, negative 0.48 correlation. Again, considered moderate negative correlation, but for our example, I'm going to let it go because it's not 0.8 or 0.9, which I think would be probably more troubling. And the last one gives us 0.08 negative correlation. That was the one that looked like such a mess in the plot, and it is because there is no correlation there. All right, so we're going to go ahead and forge forward. And now that this is done, what decisions can we make about our model? How do we build our model? So let's assume that all 3 of these fields were good candidates for our model and that there was no collinearity. So now we can build our model. So in the past, we've used the LM command. And the LM command is for linear model. And the linear model command, as I indicated in a previous video, is used for many, many, many different things. It can be used for single variable regression. In this case, we're going to use it for multiple variable regression. But what we're going to do, instead of just dumping it out to the screen and finding out what our intercept and our coefficients are, is we're going to drop it into something called cars.model. So we'll go ahead and run the same LM command, and it's going to look very familiar to you from your previous LM command. We'll just drop the results into cars.model. So we run an LM command. The price is our dependent variable, and we are comparing that to age, plus kilometer plus weight. It's not really adding age to kilometer to weight. That is just the linear model sort of syntax that you'll use to indicate that you have more than one variable in your linear model. You have more than one independent variable. So you specify age, you specify kilometer, you specify weight, and when you put the plus sign in between them, it knows to combine those and use those to actually make predictions for price. The data set is equal to train.df, which is great, that's all fine. So we'll go ahead and run that. And when we run it, doesn't look like it does anything because it drops everything into cars.model. Okay. Now we want to go ahead and show what the results are in cars.model. We set this options to scipen equals 999 to limit the number of decimals. That is a command that limits the number of decimals that show in the display. Then we can go down and show the results of what's actually in cars.model. And this is what it gave us. Okay, it looks like kind of like a lot of information, but let's go through what it means. First things first is our command. Linear model formula, we've seen this. This is what we just ran. This is what generated this. Our residuals, I'm going to have you skip over that. Don't worry about that. We're going to come down here to coefficients. Okay, what do we have? We have coefficients, our intercept. Our intercept is 2095.185143. Remember that our intercept is the point at which our trend line, if we were to draw one, would cross the vertical axis. At this point, that's kind of not really all that important because we just know we have to include the intercept in our calculation, in our formula, in order to actually have an accurate estimate of what the price is going to be. Our coefficients for age, kilometer, and weight are listed here. 135, negative 135, negative 0.023, and then 16.418. We are going to use these three things when we build our calculation. Okay. Down here you have significance codes, and the significance codes are indicators of, and we talked about p-value already, but the p-value, what's the p-value? What's the level of confidence we have in the data set? Or conversely, how likely is it that we got these values purely by chance? It's extremely low, extremely low. So we have good confidence that these values are something that we can trust. Down here, residual standard error, multiple R squared, F statistic. These are statistical terms. If you're familiar with them, you'll see that what they really mean is that our model is accounting for 82.54% of the variability in the data, which is really good, and that our F statistic is very high on a very good p-value. These are just they're statistical measures of how confident we can be in our model, and the reality is right now you don't need to worry about them. There are four things you need to worry about in this data set, or in the summary, and that is the intercept and these three coefficients. Okay. We'll have them there, and we don't need to like write them down or anything, but we'll have them. And now we're going to build our model. Okay, so like we'll go back over to our script, and like I say in the command or the comments, we now have an intercept and a coefficient or slope for each variable. We can build our model by plugging in the intercept and the coefficients directly into our model. The intercept should be singular, and I'm going to make it singular because we only ever have one intercept. We have one intercept and three coefficients. We are establishing a variable in our train.df called predicted value and populating it with our equation. This is similar to what we did in our single variable model. Okay, so I'm going to actually bring this over and sort of expand this because it goes beyond. There it is. Okay, here's what we're doing. We're saying that we're creating in our data set, our train.df data frame. This is our training set. We're going to create a new variable called predicted value. It's just what we did in the last script when we did it last week. It's going to be equal to my intercept. There's my intercept, and I popped it over there, and it goes in first. Then I add it to the train df age. That's the age variable, right? So for every one of my 600 records, I'm going to be doing this. It'll know to do it in order. So train.df $age times the coefficient for that. And we close that into parentheses, and we add that to the next one. The next one is train.df.kilometers. It's going to be multiplied by its coefficient, which is over here, 0.023021 negative. And then we close that out with parentheses, and then we add that to the third variable. The third variable is train.df weight times 16.418368. Okay, this is our model. And our model is basically built by looking at the 600 records we had in the training data set and saying the relationship between age and price, kilometers and price, weight and price, we can establish patterns with those three variables in conjunction and give them those coefficients such that when we add it to the intercept, it's going to yield us a very strongly predicted price. So that's what we're doing. So let's go ahead and run that. All right, and we'll go ahead and we can take a look at it. But what we're doing here is when we do our train, instead of looking at everything that is in the training data set, which is what we would normally do with the view command, we're going to narrow it down. Again, we're going to use the square brackets. We're going to say, give me everything, so all 600 rows, but only give me the price and the predicted price. So I can look at them side by side. So that's pretty cool because that's pretty easy to read. So we'll go ahead and run that. And we get our predicted value and we get our price. And now we can look at them side by side. And we see that it looks pretty good. I mean, some of them are off, right? You know, every model is going to have some amount of error, but they're not off as much as you might think. Now, the first one is off kind of a lot, but the other ones they're pretty close. And you can see they kind of follow a pretty good pattern. So we have a pretty good model, it looks like. It looks like we're able to come up with some good predictions for what we think the cars are going to sell for when we actually finally sell them. All right. One more step we might do is we might want to say, okay, what's the actual error that we get? So we're going to go ahead and average the error. First of all, I got to calculate it because I kind of got ahead of myself a little bit here. Let's see, that's the view. Now we're going to average the error. I don't think we've got to that point yet. Yes, we're up here. Okay. So the next thing we're going to calculate error. So we're going to say for training data frame $ errors, we're going to create a brand new variable, brand new column that's called error, and it's going to be set equal to the train predicted value minus the train price. So whatever we came up with the predicted value minus the price is going to wind up being the error, and then we can view that. And when we view that, we'll look at the price, we'll look at the predicted price, and we'll look at the error. So let's go ahead and run through that section. Now we have our error, and we can see that the errors are all kind of all over the place. Now, I had indicated in previous conversations with you that there are 5 main ways of looking at error. And what we can do is we can convert these over to be absolute values, and we can calculate the mean, we can calculate the sum, we can calculate them as a percentage. It depends on the researcher's or the data analyst's preferred way of being able to sort of assess the value or the accuracy of the model. I'm going to have you do something that's probably the least accurate, probably the least useful. I'm just going to have you calculate the mean of the error values. So I'll go ahead and close out this and go back to our script. And that's what we're doing here. Calculate the error. We'll talk more about sophisticated ways of using error later, but right now we're just going to do the mean of train.df $error. So we'll go ahead and pop that in there. And it gives me a value. And again, like I said, not terribly sure how useful that is. One thing that actually might be useful is that we compare our predicted price to our actual price. So if we compare the predicted price to the actual price in a scatter plot, what does that look like? Let's take a look at that. That looks pretty good, right? If we were to draw a trend line through the middle of that, everything would look pretty good there. And we can have a lot of more confidence that the predicted value that we can come up with is going to be our very close to our price. And then the last thing we're going to do is we're going to do a correlation. What is the correlation of our predicted price, our predicted value to our price? That will give us another measure of how well we think our model was. And it's coming in at 0.908 or 0.91. As correlations go, that's pretty darn high. So we're in good shape. We've got a pretty good model. Now, why we built this model, how are we going to use it? Well, we have 1,000 records in our file, but what if we had data coming in all the time, and we have all these used Toyota Corollas, and we're trying to figure out what the right price should be for each one of these Toyota Corollas. And we got this data file that has 39 columns and it has 10,000 rows, and we don't want to sit there and meticulously go through what we should try to price these things out as, because we don't, we have some history of what the old ones sold for. Well, now we just apply the model. We apply the model to the new list of 10,000 records, and we come up with a very good suggested price of what we think that car is actually going to sell for. All right, so that's the practical use of the model. So I sort of left this kind of half done though. We got all the way through where we're calculating the correlation of the training or the price versus the predicted price. But now you have an assignment, and your assignment this week is to go through and do a whole bunch of stuff to the script. And I've got it all in comments right here. So let's just run through it. you're going to modify, you're going to do two things. One thing, you're going to modify the model to drop the weight variable. So that means you have to go through all of the places where we specify weight and remove it. So once you do that, then you're going to apply it to the training data set and give me the intercept and the coefficients. So I've given you the command there to calculate the adjusted price by applying, that's not really the command, that's the instructions, instructions. Calculate the adjusted price. So adjusted price is going to be the variable that you create, and you're going to apply the model in the same way that I calculated the predicted value, just without weight. So calculate the adjusted error the same way that I did for by subtracting price from adjusted price, and then calculate the mean of the adjusted error and turn that in. Okay, so there's three things I've asked you to do there. I've asked you to first drop the weight from the training set, and then basically you're going to build a model with only two variables. And then you're going to calculate the adjusted price, the adjusted error, and the mean of the adjusted error. Okay. The next thing you're going to do is you're going to go back to things, go back to kind of the beginning, and you're going to check your first model against your validation data. So we're going to we only did the training data, and now we're going to go back to the beginning and we're going to use the validation data. So you're going to use the model that still has three variables in it. So we're going to go back to using the weight variable, the weight kilometer, and the age variables will all be included in this. And you're going to calculate your predicted value and your error in your valid DF data frame. So in this case, what you're doing is all the places where I had specified train.df, your job now is to specify valid.df. So I want you to, you're basically running the same model and seeing how different it is when you use a validation data frame. So go ahead and average the error, and then how does it compare to the average error in train.df? How close were we? Okay, so you have 6 things that you're to turn into me. The average error in train.df with all 3 variables in the model, I gave you that one. The intercept and coefficients when you drop the weight out of the model and apply it to train.df, and the average error in train.df with just age and kilometer in the model. Then go ahead and switch over to valid.df and run the 3 variable model against valid.df. Calculate predicted value and error using the data at valid.df. So the items 4, 5, and 6 that you're going to turn into me are going to be average error in valid.df with all 3 values in the original model. A plot of the price against the predicted value in value.df. Remember how we did that at the last part to show the pretty nice, pretty slick scatter plot that would be very nice around a trend line. So you're going to go ahead and run a plot of that, again, just using the valid.df set. And then the correlation. What is the correlation coefficient when you compare the valid.df $price versus the valid.df $predicted value in valid.df? Okay. There's a lot there. This video has gone for almost 33 minutes, so hopefully there's enough information in there. If you have any questions, don't hesitate to ask me. If you have one thing that really helps me is if you have questions, if you can send me your script so I can see what you're doing, or send me a screenshot of your script, and then I can help you work through any challenges you have. But hopefully you'll be able to get through all this, and you'll be able to not only have last week built your first predictive model in R, but now you're building your second predictive model. It's just a multiple variable linear regression model. All right, good luck.